Hello, in this lecture we find out the area of a circle. In the drawing we have a semicircle. Inside this semicircle we have this circle, and our mission is to find out the area of this circle. In addition, we know that line segment AQ equals to 2 units in its length. This is line segment PB. This is line segment TB. This equals to 8 units in its length. This is angle PQA, that is a right angle, and this is angle STB, that is also a right angle. Again, our mission is to find out the area of this small circle. Okay, so first of all, this is a semicircle, and therefore AB is the diameter of this semicircle. So AB is a diameter, it is absolutely a straight line. So if we focus on the upper side of this straight line AB, at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. That's the sum of the angles. That says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of AB at point Q? We have this angle that is equal to 90 degrees in size, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, if we focus on the upper side of the straight line AB at point T, here the sum of the angles must be also equal to 90 degrees. The sum of the angles in the upper side of AB at point T must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of AB at point T? We have this angle that is the right angle plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will define the relevant points to this question with letters. We will define the center of this big semicircle, this point, as point H. We will define the center of this small circle, this point, as point K. And we will define the point of tendency of tangent AB with this small circle. This point is point M. We join points K and M together by a straight line. What is the definition of line segment KM? Line segment KM starts from point K, that is the center of this small circle, and then at point M, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore, KM is the radius of this small circle. We define the radius of this circle as x. So Km equals to x. Here we can implement rule 1. I'll repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius along to its point of tendency. In the drawing we have a circle, and we have tangent AB. This is tangent AB, that is tangent to this circle at this point, point M. And we have the radius OM, that is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. So can I fully implement rule 1 in our drawing. In our drawing, we have the radius Km, that is 1 to point M, that is the point of tendency of tangent AB with this small circle. Whenever you have a radius that is 1 to the point of tendency, then tangent AB will be perpendicular to the radius MK. If AB is perpendicular to MK, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Okay, so we will define the point of tendency of tangent ST with this circle, this point, as point Z. And we join points K and Z together by a straight line. Line segment KZ is the radius of this circle, that is equal to x according to our definition. Again, we have the radius KZ that is on to point Z, that is the point of tendency of tangent ST with this small circle. And whenever we have a radius that is on to the point of tendency, then tangent ST will be perpendicular to the radius ZK. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So here we created a quadrilateral KZHM. Again, we created a quadrilateral KZTM. Inside quadrilateral KZTM we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, and 270 degrees plus the size of this 4 pieces again, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore these 4 pieces again must be equal to 90 degrees in its size. So inside quadrilateral KZTM we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we will write this quadrilateral KZTM as a rectangle, but we also know that the opposite sides of a rectangle are equal to each other. So a rectangle KZTM, side KZ must be equal to the opposite side MT. But KZ is x, therefore MT must be also equal to x. Likewise, in the same rectangle KMTZ, side KM must be equal to the opposite side ZT. But KM is x, therefore ZT must be also equal to x. So we should find out that quadrilateral KZTM is not a rectangle but a square, because all of its sides are equal to each other. Each side of this square is equal to x. So I write it down. We found out that quadrilateral KZTM is a square. We define the point of tendency of tangent PQ with this small circle, this point, as point L. We join points K and N together by a straight line. KL is the radius of this circle that is equal to x according to our definition. Again, we have the radius KL that is on to point L, that is the point of tendency of tangent PQ with this small circle. Whenever we have a radius that is on to the point of tendency, then tangent PQ will be perpendicular to the radius LK. If PQ is perpendicular to LK, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside quadrilateral KLQM we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. 470 degrees plus the size of this fourth missing angle, in total the must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. 60 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So quadrilateral LKMQ has 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral LKMQ is a rectangle, and we know that the opposite sides of the rectangle are equal to each other. So in rectangle LKMQ, side LK must be equal to the opposite side MQ, but LK is x, therefore MQ must be also equal to x. Likewise, according to the same rule, the same rectangle LKMQ, side KM must be equal to the opposite side LQ. But KM is x, therefore LQ must be also equal to x. Again, we can find out that quadrilateral LKMQ is not a rectangle but a square because all of its sides are equal to each other. So, what is the size of angle ZKL? The size of angle ZKL equals to 90 degrees plus 90 degrees, it is 180 degrees. And we know that any angle that its size is 180 degrees, it is defined as a straight line. So, therefore, ZKL is a straight line. ZKL is a straight line. If ZKL is a straight line, it means that ZL is also a straight line. ZL is a straight line, and therefore, shape LKTQ is a quadrilateral. Why? Because this shape LZTQ has 1, 2, 3, 4 sides, and therefore it is a quadrilateral. So inside quadrilateral LZTQ, inside this quadrilateral, we have 1, 2, 3, 4 right angles. Therefore, we relate to quadrilateral LZTQ as a rectangle, and you also know that the opposite sides of a rectangle are equal to each other. So in rectangle LZTQ, side LZ must be equal to the opposite side TQ, but LZ is 2x, therefore TQ must be also equal to 2x. Actually, LZ is a straight line that touches the circle at 2 points, L and Z. Therefore, LZ is a chord. LZ is a chord that passes through point K, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, LK is the diameter of the circle. So I write it down. I found out that LK is the diameter of the circle. And it is equals to 2x. And because of the fact that LZTQ is a rectangle, side LZ must be equal to the opposite side QT. But LZ equals to 2x, therefore QT must be also equal to 2x. Here QT equals to 2x. Okay, what is the radius of the semicircle? The radius of the semicircle equals to the diameter AB over 2. Okay, we define the radius of the semicircle as capital R. So capital R equals to the diameter that is AB over 2. But what is the length of the diameter AB? From the drawing it is very easy to see that the diameter AB in total equals to 2 plus 8, that is 10. 2 plus 8 is 10. plus 2x. So in total, the diameter AB equals to 10 plus 2x. Here AB equals to 10 plus 2x, and therefore the radius equals to 10 plus 2x over 2. 10 plus 2x over 2 is 10 over 2, that is 5, plus 2x over 2 is x. So in total we found out that the radius of the semicircle capital R equals to x plus 5. Okay. Here we have an internal notch between the big semicircle and this small circle. That is to say, the two circles touch each other internally at this point. Okay, and whenever you have an internal notch between two circles, you can implement rule 9. Repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching point. We have here two circles, and those two circles touch each other internally at this point, point P. The radius of the big circle is 0 at point O. The radius of this small circle is 0 at point M. And the straight line that connects the centers together is of course the straight line OM. And according to this rule 9, the straight line OM must pass through point P, that is their touching point. Again, the straight line OM must pass through point P. Or OMP is one straight line. Again, OMP is one straight line according to this rule 9. So we can implement rule 9 in our drawing. Why? Because in our drawing we have an internal notch between this small circle and the big semicircle. That is to say, they are touching each other internally at this point. And therefore, according to rule 9, the straight line that connects their centers together must pass through their touching points. The center of the big semicircle is here at point H. The center of this small circle is here at point K. And the straight line that connects their centers together is of course the straight line TK. And the straight line TK must pass through their touching points. So enjoy points T and K together by straight line, and the straight line TK must pass through their touching points. Okay. You can see from drawing that the straight line HK passes through their touching point. We define the touching point as point G. Repeat, you can see from the drawing that the straight line HK that connects their centers together passes through point G, that is their touching point. Or edge KG is one straight line. Again, edge KG is one straight line according to rule 9. If edge KG is one straight line, it means that edge G is a straight line. But what is exactly the definition of the straight line edge G? The straight line edge G starts from point H, that is the center of the semicircle, and then at point G, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, edge G is the radius of this semicircle. So write it down. Edge G is the radius of the semicircle, and the radius of the semicircle equals to x plus 5. Repeat again, the radius edge G of the semicircle equals to x plus 5 units in its length. What is the definition of line segment KG? line segment KG starts from the center of this small circle, that is to say from point K, and ends at point G, that is a point on the small circle itself. So this is exactly the definition of a radius. Therefore KG is the radius of this small circle, that is equal to x according to our definition. So what is the length of the missing side edge K? The length of the missing side edge K equals to edge G minus KG. Again, edge G minus KG equals to the missing side edge K. So I write it down. The missing side edge K equals to edge G minus K edge minus K edge. So the missing side edge K equals to edge G, that is the radius of the semicircle, that is equal to x plus 5, minus K edge, that is the radius of the small circle, that is equals to, actually it is equals to minus Kg, that is the radius of the small circle, that is equal to x. Repeat again. The missing side K edge equals to edge G minus Kg. Edge G is x plus 5, Kg is x, and x plus 5 minus x equals to 5. So actually found out that the missing side edge K equals to 5 units in its length. So write it down, edge K equals to 5 units in its length. What is the length of the missing side M edge? From the drawing it is very easy to see that M edge equals to A edge, that is the radius of the semicircle, A edge minus AQ minus QM equals to the missing side M edge. So I write it down, M edge, the missing side M edge equals to A edge, that is the radius of the semicircle, minus AQ minus QM. So the missing side M edge equals to A edge, that is the radius of the semicircle, that is equals to x plus 5 minus AQ is 2 minus QM equals to x. So in total the missing side M edge equals to x plus 5 minus x is x, and 5 minus 2 is 3. So the missing side M edge equals to 3 units in itself. M edge equals to 3, so I write it down, M edge equals to 3 units in its length. In the next step I'll copy the right green triangle KM edge in a new page, and we'll implement the Pythagoras theorem on this right green triangle KM edge. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a version for Pythagoras theorem. So actually, this is the right triangle KMH that I copied from the original drawing. The hypotenuse KH equals to 5 units instead. We just right now found out that MH equals to 4 units instead. And Km equals to x. It is the radius of the small circle. According to the Pythagoras theorem, in this right triangle KMH, KH square equals to KM square plus MH square. Again, KH square equals to KM square plus MH square. So I write it down. KH square, that is the square of the hypotenuse, equals to Km square plus MH square. The hypotenuse KH equals to 5, therefore KH square is 5 square, that is 25. And it is equals to Km square. Km is x, therefore Km square is x square, plus Mh square. Mh is 3, therefore Mh square is 3 squared, that is 9. So in conclusion, according to Pythagoras theorem, we found out that 25 equals to x square plus 9. Here we subtract 9 from this equation, and finally we get that x square equals to 25 minus 9 is 16. X square equals to 16. We take out of this equation and we get that x equals to the square root of 16, that is 4. The radius of this small circle x equals to 4 units in its length. Our mission is to find out the area of this small circle. We know that the area of any circle equals to pi times the radius square. Again, the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle, that is the area that we are looking for in this question, will be equal to pi, and the radius square is x squared, that is 16. So it is pi x squared. X is the radius, therefore x squared is the radius square. So pi x square is the area of the circle. So the area of the circle equals to pi, and x squared is 16. We substitute x squared by 16. So in conclusion, we found out that the area of this small circle equals to either 16 pi square units, or in terms of numbers, it is equals to 50.265 square units. I'll repeat again. Actually found out that the area of this small circle that is located inside the big semicircle, it is equals to either 16 pi square units, or in terms of numbers, it is equals to 50.265 square units. Okay, so in the next step, I will summarize the lecture. So in this lecture, I found out the area of this small circle. This small circle is located inside the big semicircle. We know that this is line segment AQ, that is equals to 2 units in its length. This is line segment TB, that is equals to 8 units in its length. This is angle PQA. This is angle PQA, that is the right angle. And this is angle STB, that is also a right angle. Repeat again that our mission is to find out the area of this circle. Okay, so first of all, we know that AB is the diameter of this semicircle. AB is a diameter, it is absolutely a straight line. So if we focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. That states that the sum of the angles on one side of a straight line is equal to 180 degrees. In our specific case, it means that the implementation of the rule is as follows. The sum of the angles on the upper side of the straight line AB at point Q must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of AB at point Q? we have this angle that is the right angle plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Likewise, if you focus on the upper side of AB at point T, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of AB at point T? We have this angle, that is the right angle, plus the missing angle. In total, they must be equal to 180 degrees. So this missing angle must be equal to 90 degrees in its size. Okay. In the next step, we defined the relevant points to these questions with letters. We defined the center of this big semicircle as H. This is the center of the semicircle that we defined as H. We defined the center of this small circle, this point as K. We define the point of tendency of tangent ST with this small circle, this point as Z. We define the point of tendency of tangent PQ with this small circle, this point as point L. And finally, we define the point of tendency of tangent AB with this small circle, this point as point M. Here we can implement rule 1. Actually, in the next step we join points K and M together by side line. Km is the radius of the circle. We define the radius of this small circle as x. The radius Km is drawn to point M, that is the point of tendency of tangent AB with this small circle. And whenever a radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MK. If AB is perpendicular to MK, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we join points K and L together by side line. KL is the radius of this circle that is equal to x according to our definition. The radius K, sorry, it is KZ. KZ is the radius of this circle that is equal to x. The radius KZ is drawn to point Z. Therefore, according to rule 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. So inside the quadrilateral KZTM, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral KZTM, we have 4 right angles, and according to rule 6, any quadrilateral that has 4 right angles must be a rectangle if not a square. So we'll relate this quadrilateral KZTM as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle KZTM, side KZ must be equal to the opposite side MT. But KZ is x, therefore MT must be also equal to x. Likewise, in the same rectangle KZTM, side KM must be equal to the opposite side ZT. But KM is x, therefore ZT must be also equal to x. So we found out that quadrilateral KZTM is not a rectangle but a square because all of its sides are equal to each other. Likewise, we join points K and L together by side line. KL is the radius of this circle that is equal to x. The radius KL is drawn to point L, therefore, according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So we created a quadrilateral KLQM. Inside quadrilateral KLQM, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the quadrilateral KLQM, we have 4 right angles. Therefore, we relate to this quadrilateral KLQM as a rectangle according to rule 6. But we also know that the opposite sides of a rectangle are equal to each other. That is to say rectangle KLQM, side KL must be equal to the opposite side QM. But KL is x, therefore QM must be also equal to x. Likewise, according to the sum rule, in the sum rectangle KLQM, side KM must be equal to the opposite side LQ. But KM is x, therefore LQ must be also equal to x. So we found out that quadrilateral LKMQ is not a rectangle but a square because of the fact that all of its sides are equal to each other. We have here angle ZKL. This is angle ZKL. This angle ZKL equals to 90 degrees plus 90 degrees, then 180 degrees. Therefore, we know that any angle that is equal to 180 degrees in its side, it is defined as a straight line. Therefore, ZKL is a straight line. If ZKL is a straight line, it means that ZL is a straight line. So ZL is a straight line, but it is a straight line that touches the circle at 2 points, Z and L. Therefore, ZL is a chord. ZL is a chord that passes through point K, that is the center of the circle. And you know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, ZL is the diameter of the circle. ZL is the diameter of the circle, and it is equal to x plus x, that is 2x. So, ZL is the diameter of the circle, that is equal to 2x units in its length. Okay, anyway, ZL is a diameter, it is absolutely a straight line, and therefore the shape LKTQ, this is the shape LKTQ, it is a quadrilateral because it has 4 sides, 1, 2, 3, 4. But it is a quadrilateral with 4 right angles, 1, 2, 3, 4. And you know that according to Rule 6, any quadrilateral that has 4 right angles must be a rectangle, not a square. So we relate to this quadrilateral LZTQ as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle LZTQ, side LZ must be equal to the opposite side TQ. But LZ is 2x, therefore TQ must also equal to 2x. Okay. Then we found the missing side, side M edge. Although it is very easy to see that M edge equals to A edge, it is the radius of the semicircle, minus AQ minus MQ. Repeat again, the missing side, side M edge, the missing side, side M edge equals to A edge minus AQ minus MQ. So M edge equals to A edge, that is the radius of the semicircle. Actually, the radius of the semicircle equals to x plus 5 minus AQ, that is 2, minus QM, that is x. QM is x. So in total, the missing side M edge equals to x plus 5 minus 2 minus x. X plus 5 minus 2 minus x is 3. So the missing side M edge equals to 3 units in its length. So we found out of 3 also that the radius of this semicircle, capital R, equals to x plus 5. Why? Because the radius of the semicircle equals to the diameter AB over 2. The radius capital R of the semicircle equals to the diameter AB over 2. The diameter AB in total equals to 2 plus 8, that is 10 plus 2x. Again, the diameter AB equals to 10 plus 2x. Again, the diameter AB equals to 10 plus 2x. And if we divide the diameter by 2, we get the radius R. So the radius R equals to AB, that is 10 plus 2x over 2. 10 plus 2x over 2, 10 over 2 is 5, and 2x over 2 is x. So in total, the radius of this semicircle, capital R, equals to x plus 5. Okay. So here, we can implement rule 9. Why? Because we have an internal lunge between this small circle and the big semicircle. That is to say, they are touching each other internally at point G. Whenever you have an internal lunge between two circles, you can implement rule 9. I'll repeat quickly on rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together must pass for their touching points. Those two circles touch each other internally at point P. This point is point P. The center of the big circle is 0.0. The center of this small circle is at point M. And the straight line that connects the centers together is of course the straight line OM. And according to this rule 9, the straight line OM must pass for point P. That is their touching point. Or OMP is one straight line. Again, OMP is one straight line according to this rule 9. We can actually implement rule 9 in our drawing. In our drawing, you have internal edge between the big semicircle and the small circle. That is to say, they are touching each other internally at point G. Point G is their touching point. The center of the big semicircle is 0 at point H. The center of this small circle is 0 at point K. And the straight line that connects the centers together is of course the straight line HK. According to rule 9, the straight line HK must pass for point G, or edge KG is one straight line. Again, according to rule 9, edge KG is one straight line. If edge KG is one straight line, it means that edge G is also a straight line. But what is the definition of the straight line edge G? The straight line edge G starts from point H, that is the center of the semicircle, and at point G, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore, edge G is the radius of the semicircle. This is equal to x plus 5 units in its length. What is the definition of line segment KG? Line segment KG starts from point K, that is the center of this small circle, and then at point G, that is the point of the small circle itself. So this is exactly the definition of a radius. Therefore, KG is the radius of this small circle, that is equal to x. Therefore, in total, we know that HKG is one straight line, and therefore the missing side HK must be equal to edge G minus KG. Again, edge G minus KG equals to the missing side HK, because HKG is one straight line. Again, the missing side HK, the missing side HK must be equal to edge G minus KG. Okay, so the missing side HK equals to edge G, that is the radius of the missing side HK, the missing side KH or HK equals to the radius of the quarter circle, that is edge G minus KG. So the missing side KH equals to the radius of the semicircle, that is x plus 5 minus KH, that is the radius of the small circle, that is x. So in total, the missing side KH equals to x plus 5 minus x. X plus 5 minus x is 5, because x minus x is 0. So we found out that this is the missing side KH, that is equals to 5 units in its length. We have already found out that MH equals to 3 units in its length, and KM equals to x, it is the radius of this small circle. In the next step, I copied this right green triangle KMH in a new page, and we implemented the Pythagoras theorem on this right green triangle KMH. This is the right green triangle KMH that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle KMH, KH square equals to KM square plus MH square. Again, KH square equals to KM square plus MH square. KH is 5, therefore KH is 5 squared, that is 25, and it is equal to KM square. KM is x, therefore KM square is x square plus MH square. MH is 3, therefore MH square is 3 square, that is 9. So in total, we found out that according to the Pythagoras theorem, in the right triangle KMH, 25 equals to x square plus 9. We subtracted 9 from this equation, and finally we found out that x squared equals to 25 minus 9, that is 16. So x squared equals to 16. We took out of this equation, and finally found out that x equals to the square root of 16, that is 4. The radius of the small circle, x equals to 4 units in itself. Our mission is to find out the area of this small circle. And we know that the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle, our small circle, will be equal to pi times the radius of the circle squared. The radius of the circle is x, therefore the radius of the circle squared is pi x squared. We just right now found out that x squared equals to 16, so we can substitute x squared by 16. In this equation, if we substitute x squared by 16, and found out that the area of the circle equals to pi times 16 square units, or 16 pi square units, or in terms of numbers, the area of this small circle equals to 50.265 square units. I'll repeat again, we actually found out that the area of this small circle equals to either 16 pi square units, or in terms of numbers, it is equals to 50.265 square units. Okay, thank you very much.